Welcome to my presentation. My report's name is Memory-Centric Communication Mechanism for Real-Time Autonomous Navigation Applications. I'm Wei Liu from Too Simple. I'll give this presentation with the following aspects: background and motivation, virtual layer-based architecture, pre-record memory allocation algorithm, and evaluation. As we know, there has been a remarkable increase in speed of artificial intelligence development, especially in computer vision, natural language processing, and reinforcement learning. With the evolution of deep learning, intelligent autonomous navigation system grows rapidly. To improve the system robustness, security, and fast deployment, resource isolation and modularity is needed. The autonomous navigation system consists of various processes of operating system, including C++ implementation and Python implementation, especially for deep learning module. With multi-process model, we have many advantages, such as resource isolation, modularity, and cross multi-language boundary supporting. And this model has its disadvantages, such as latency introduced by inter-process communication. At the same time, memory throughput will become high due to memory movement. In autonomous driving environment, such latency could cause long bucking distance and out-of-date perception result, which could finally affect the planning decision. Here, I demonstrated a typical simplified autonomous navigation system. It includes diversity of sensors, localization, perception, planning, and control modules. Each module is isolated process with publish-subscribe semantics. Excepted the module's calculation time consuming, the IPC cost is not neglectable. In a real-world workflow, the total IPC cost can be up to 20% of the total latency. The second graph demonstrated a typical socket-based IPC procedure, like those two. In terms of those two, the publish process generates a message from the language interface layer and then convert it to the middleware representation, serializing it to the transport layer before write to the socket buffer with the help of the operating system. At the right-hand side, the subscribe process reads the bytes from the socket buffer, then deserialize it to the language-neutral middleware representation. After that, the subscribe process deconvert it to the language-specific message. We studied the details of the IPC cost in those two-like framework in both C++ and Python processes. We select two types of methods, image and waypoints. Image is with a plain structure, and waypoints is a multi-level nested structure consists of large numbers of small-size objects. The breakdown of IPC latency can be classified into memory allocation, serialization, and deserialization, memory copy, convert, and deconvert phases. We observe that for image, memory allocation cost can take up to 30% and 6% of the total cost for C++ and Python respectively. For waypoints, the converting cost of passing can take up to 90%. Based on this observation, we summarized that the total IPC cost can be divided into two parts, that is, memory allocation cost and data movement cost, which including memory copy, convert, and deconvert. To improve the IPC performance, we designed a memory-centric mechanism to reduce both memory allocation and data movement costs. We propose and implement a virtual layer-based architecture to avoid unnecessary memory allocation and data movement between multi-layers for language boundings and data representation. Furthermore, we propose a pre-record memory allocation algorithm to improve the efficiency of memory allocation. Here, we call it a Z framework. In order to address those performance problems, we designed a new architecture called virtual layer-based architecture. The left side figure shows an architecture of those two. The right figure shows the virtual layer-based architecture. The interface layer is a virtual layer, and the date in layer is a wrapper. The real data is in the middleware layer and is pointed to by the interface layer. The transport layer is another virtual layer as well, where the real data is in the shared memory and can be shared with other processes. By introducing virtual layer-based architecture for passing processes, the converting from interface layer to middleware layer can be avoided. The memory copy for transport layer to the socket buffer can be avoided for both C++ processes and passing processes. From the implementation perspective, we utilize the PY band mechanism to implement the virtual interface layer for passing. For C++, the memory pointer can directly used in virtual interface layer. The message is actually stored in middleware layer, and we offer passing methods and interfaces to read, write, and modify the message. We adapt it as a bridge to connect the message interface and the inner data structure. In order to implement the virtual transport layer in our system, a shared memory mechanism is necessarily adopted. We designed a shared buffer with ring structure in association with its publisher and subscriber, as shown in this figure. It consists of two parts, management part and data part. Management part stores the global information of the shared buffer, while the data part stores the elastic data, shown as slots. The definition of variables in management and data part are shown in the tables. It is used to control the publish and subscribe procedure. The date is transferred by shared memory, and the notification mechanism utilizes the process shared mutex and condition variables. To improve the parallelism, we use a read count and write flag to implement the cross-process read-write lock. Data movement cost can be largely reduced. However, in the middleware layer, the memory allocation cost can still largely affect the performance of IPC. We analyzed the root cause of it and found the pitfall reason. After that, we adopt a cost model to guide the optimization and propose to utilize memory pool and pre-record memory allocation algorithm for memory allocation performance optimization. In the publishing process, we keep an object map to hold the objects. When the memory allocation is invoked, we first inquire the object map to obtain the total size. If the key is not found, the memory will be allocated recursively and the value will be assigned and saved in the object map. Otherwise, the memory can be directly allocated from the memory pool. In the subscribing process, we first pre-read the message and obtain the metadata. When we can allocate the memory from the memory pool directly, we further propose several optimization techniques to supplement our autonomous navigation system, such as efficient data assignment and efficient data extraction for continuous memory block. Sometimes we may need to pass messages across machines' boundary, and in that condition, we will switch to the socket mode. To validate our proposed method, we evaluate the performance of the framework from a comprehensive perspective. We evaluate transmitting image message with size from 256 kilobytes to 8 million bytes. The result showed that the framework can significantly outperform those 1, those 2, and CyberRT. For C++, it's mainly because the memory pool technique can reduce the pitfall costs. For Python cases, comparing with those two, the PY band design advantage is clear. We select 4 different types of messages used in our real-world system and evaluate IPC costs for each type. The result shows that the framework can largely outperform other frameworks for all types of messages. To evaluate the performance effects of techniques that are applied in the framework, we here analyze each technique that contributes to the performance improvement. The yellow bar shows the benefit gained by virtual layer-based architecture, and the blue bar shows the benefit from the pre-record memory allocation algorithm. Those 2 plus VML can significantly outperform those 2 with the performance improvement of 10 to 50% for different types of messages because of the shared memory technique. Comparing with those 2 plus VML and the framework, we note that messages with large size have a larger performance improvement than the messages with small size. It indicates that our memory allocation optimizations are more useful for the data with large size. Finally, we studied the performance of different frameworks in a real workflow. We measured the end-to-end IPC latency and the data movement throughput. We observed that the framework can largely outperform other frameworks in the workflow, which benefits from our proposed memory-centric techniques. The latency of those 2 and CyberRT are similar. In addition to total latency, By measuring the memory throughput of message passing with PCM, we observe that this framework and CyberRT can largely reduce the throughput from 70 gigabytes per second to 5 gigabytes per second by shared memory technique compared to socket-based IPC methods. Benefiting from PUI band techniques, this framework can reduce about 10% data movement throughput compared to CyberRT. This memory throughput decrease will significantly alleviate memory-insensitive algorithm modules which prevail in autonomous navigation systems. Thank you very much.